this video, we will continue to explore patterns of inheritance. Recall that we have two sets of chromosomes, one from our mother and one from our father. Each person passes on one set of their chromosomes to their child. Which chromosomes are a part of this set is just chance. This person might pass on the chromosome 1 they got from their dad and the chromosome 2 they got from their mom. The two chromosomes of each type, one from each parent, have the same genes in the same locations. So we have two copies of each gene. A gene determining our blood group is on chromosome 9. Again, we have two copies of this gene. A gene affecting our hair color is on a different chromosome, chromosome 16. A person might have an allele for blood group B from their mom and an allele for blood group O from their dad. On a different pair of chromosomes, they might have an allele for light hair and an allele for dark hair. There are 4 possible combinations of alleles they could pass on to their child: B and light hair, O and light hair, B and dark hair, or O and dark hair. Which allele the child inherits for blood group does not depend on which allele the child inherits for hair color. These genes are inherited independently. To reiterate, these genes are inherited independently because they are on different chromosomes. What if the genes were on the same chromosome instead of being on different chromosomes? Let's imagine a hypothetical scenario in which the hair color gene and blood group gene are on the same chromosome. So now, the alleles for blood group B and light hair would be on the chromosome from mom. The alleles for blood group O and dark hair would be on the chromosome from dad. An entire chromosome is usually inherited as a unit. If their child inherits an allele for blood group B, they will most likely also inherit the rest of this chromosome, including the allele for light hair. If the child inherits the other chromosome instead, they are likely to inherit both the allele for O and an allele for dark hair. We now have only 2 combinations of alleles instead of 4. The inheritance of the genes is linked since they are on the same chromosome. We call this chromosomal linkage. To recap, genes on different chromosomes are inherited independently. Genes on the same chromosome are usually inherited together. So far, we've seen that we have 2 copies of each gene. The last pair of chromosomes is an exception. Recall that males have an X chromosome and a Y chromosome. The Y chromosome is much smaller with fewer genes. Of the few genes on Y, many are unique to males and not present on X. Since most genes on X and Y are unique, males have only one copy of genes on the X chromosome. Let's explore the inheritance of genes on the X chromosome. Hemophilia is an inherited disease. People who suffer from hemophilia are unable to make their blood clot. They bleed severely from small injuries. The gene linked to hemophilia is on the X chromosome. When a gene is on the X chromosome, we write its alleles as superscripts of X. The allele causing it is recessive. People with at least one functioning allele of this gene are healthy. The normal allele is dominant. We will represent it with a capital H superscript. Consider a healthy father with one normal allele on his X chromosome. Recall that this gene is only found on X. His Y chromosome does not carry an allele. Suppose the mother is healthy but carries a recessive allele for hemophilia. The dad can pass on either capital H, the normal allele, or a Y chromosome. The mom can pass on either capital H or lowercase h. Here are the possible genotypes of their offspring. They could have a healthy female with no hemophilia allele. They could have a healthy female who is a carrier for hemophilia. Though she is unaffected, she could pass it on to her children. They could have a healthy male or a hemophiliac male. Notice that all their daughters are healthy, but their sons have a 50% chance of developing the disease. For genes only present on one of the sex chromosomes, X or Y, the likelihood of possible genotypes depends on the gender of the offspring. In the previous example, only sons had a chance of being affected. We call this sex linkage. Hemophilia is an example of a sex-linked disease. You now understand the inheritance of genes on the same chromosome and genes on an X or Y chromosome.